Well, guys, welcome back to another lecture. Hopefully you had a good Memorial Day holiday. Time to jump back into some more PLC stuff, and this week we're going to talk about number systems, and this actually is very, very important. This will be one of the most important weeks of lectures that we do. As you know, digital information is stored as groups of zeros and ones. And so we want to understand how this information is represented as zeros and ones. So we're going to learn about different types of number systems, but specifically we're going to learn about the number system that that digital devices and machines use, called machine language. You remember this document. This is the logical rack we talked about last week, and this represents the input image table and output image table, which is just kind of a way to think about storage of bits in memory. And we talked a little bit about this in the previous lecture, but I want to bring this back up. We mentioned that these two tables, this is the output image table and this is the input image table, and a good way to think about these two tables is just a bunch of slots or cells, like an Excel spreadsheet. And these numbers here, these are the bit numbers. Over here I have the type of table. This is an output image table, so I start this with the letter O. Down here I have an input image table, so I start with the letter I, so I can tell just by looking at this if I'm dealing with an output or input. And then over here we have other information, which basically this forms the beginnings of what we're going to call the address. Each one of these terminals that we talked about in previous lectures that you could connect the sensor or switch to on the PLC, each screw terminal has to be mapped to a specific location in memory. And this is a way of organizing that. So let's say I have an input module. This is the address, you can call it the address for now of the input module. So I have input module 0, 1, and then these are the bit positions. So I might have a switch connected to a certain screw terminal that's mapped to this bit position right here. And so I can actually address that by, if I know the I:01, that specifies which input module we're talking about. And then over here I can basically trace it all the way down to a specific bit position. So this number 6 right here represents a cell. The 6 is just an address, and that cell can contain a 0 or 1. And so we're able to reference that cell if I know which input card, in this case 0, 1, and if I know which slot or cell in the input image table contains that binary information, well, I can trace it, I can map it actually down to this actual bit position right here. The reason I'm actually bringing this up, though, is because when we talked about this, we looked at the numbering system here. Look at how this is numbered. This goes, it starts with 0, first of all. When I count each bit position, it starts at 0. And even when I count the output, these are the output modules, represent or reflect the output modules. Now remember, this is all in memory, so it's not a physical module, but this is mapped to a specific output module on the PLC. So output module 0, 0, and then it starts from 0 and counts up to 7. So there's 8 rows here, but notice that we start counting from 0. That's the first thing you want to make sure you understand when we're dealing with machines, numbers, and codes. All machines, all digital devices, when they count, they start the count with 0 and not 1. As humans, when we count, we start with number 1. If I'm going to count the number of, say, letters in the alphabet, I start with A, that's 1, B is 2, 3, 4, and I will count beginning with number 1. When a machine counts, that machine will always start the count with 0. So that's one important piece of information. We will always start counting with 0. We will never start counting with 1. But if you look a little bit closer at this, notice how the numbers go. We go 0, 1, 2, 3, 4, 5, 6, 7. We skip 8 and 9, and then we jump over to 10, 11, 12, 13, 14, and we go all the way up to 17. So I want to talk a little bit about this. Why is it numbered that way? What's the purpose of it? Well, if you read down here, it talks about this is kind of small print here. It says the above input and output addresses are for Allen Bradley PLCs and are in the, and then right here it says the octal numbering system. So this is a specific type of numbering system called octal. And actually we're going to talk about several types of number systems. As a matter of fact, we're going to even make up some of our own number systems, and you'll see exactly how that works. So I wanted to bring this document back up just so you can kind of have this in your mind's eye. Remember this numbering here, this weird numbering, and we won't explain this today, but in the future, very future, in a couple days when we get to the lecture, we'll come back to this numbering system called the octal numbering system, and you'll understand precisely how this works. So I'm going to start with the PowerPoint now, and I'll pause this and we'll switch over to the PowerPoint. Okay, here is our PowerPoint on number systems and codes, and this particular PowerPoint deals with the binary number system. Knowledge of different number systems and digital codes is useful when working with digital devices such as the PLC. This is true because these devices represent all data in the form of numbers. We talked about the first week the difference between analog and digital, and you understand that most quantities in nature exist in analog, but when I want to get that quantity into a machine, a digital machine, well, machines don't understand analog, they only understand digitals. And so I have to go through a process. You understand now that if I want to digitize an analog signal, that's a process. So we talked about that process numerous times. I won't go into the details of it, but you know that ultimately when you digitize an analog signal, you end up with these codes, these numbers or codes based on zeros or ones. Any information, all information that goes into any machine is represented as a number or a code. And we'll talk about the difference between a number and a code. But that's important, a very important concept, and that's why we're going to spend a week studying number systems and codes, because any information, whether it's audio, going in, let's say your cell phone, audio or video, you can take a picture or you can make a video or you can talk into your cell phone. I guess you can draw on your cell phone. Any information that goes into that cell phone or any digital device is stored as zeros or ones, machine language. And so because of that, we want to kind of delve into the thinking and the workings of these devices to see exactly how they represent information and understand the difference between a number and a code. General rules for all number systems. All number systems are based on the information on this slide. Now, what I'm going to do is talk about a number system that everybody's familiar with, and then we'll use that as kind of a model for other number systems that we'll deal with. There's two main, or I should say two most important number systems. There's the one that we as humans use. It's called a base 10 number system. We use a base 10 number system because we have 10 digits. We have 10 fingers, 10 toes, and so it's kind of natural to base our number system on 10 since we have 10 digits. So that's one important type of number system. The other very important type of number system is the one that machines use. Machines, believe it or not, are based on switches. We talked about switches on the first week of class, and we named various different types of switches. But a machine uses these basically microscopic switches called transistors to represent or to hold a value of 0 or 1. And so that type of number system is called binary. And so we're going to talk about several number systems throughout the week and different codes. But the two most important ones is base 10, the one that humans use, base 2, the one that machines use, and being able to go between the two number systems. So we'll talk about that. But this slide, this very first slide, talks about general rules for all number systems. So all number systems we can we can write kind of a representation of number systems in this form, where this B represents the base or radix, and this N is the power. And we'll have a little bit more to say about the power here shortly. The base or radix gives us information. It tells us the total number of symbols used by the particular number system. So we as humans, we use a base 10 number system. So this B here, we can think of that as a 10 raised to the nth power. So base 10, the base tells us the number of symbols used in the particular number system. So since we use a base 10 number system, the 10 symbols we use, and remember, we're going to start counting with 0, not 1. So we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all the symbols we can use in the base 10 number system. Well, what if I go beyond 9? If I go past that? If I go past that, then what happens is I got to start repeating digits. So I'm going to pause this slide. I'm going to bring in another document. And these are all on Canvas, by the way. And we're going to compare a base 10 number system to other number systems. And then we'll come back to this slide. So here's a document that basically compares different number systems. And I was just in the PowerPoint talking about a base 10 number system. So a base 10, notice we use the symbols 0 through 9, and once we get past the allowed number of symbols for that particular number system, then we start to repeat symbols. So we go 0 through 9, and so I'm out of digits now. So now I go 1, 0, 1, 1, 1, 2, 1, 3, all the way down to 1, 9. And again, once I run out of digits, then I change this to a 2, and I repeat the process. But notice the number of symbols is just, we have 10 symbols. The base tells us the number of symbols, and that's 0 for base 10, 0 through 9. And once we run out of symbols, then we start repeating. Well, I mentioned earlier in this lecture the octal number system. So look at that, compare. We noticed that when we looked at the input and output image tables, we only use 0 through 7. So 0 through 7. And once we run out of symbols, and in the base 8 number system, there's 8 symbols. Base 10, there was 10 symbols, 0 through 9. So in the base 8, there's 8 symbols, 0 through 7. And once we run out of digits for that number system, then we start to repeat, just like we did over here. We go 1, 0, 1, 1, 1, 2, all the way up to 1, 7. And then we change this to a 2, and we start the process over again. So this should make that, when you go back and look at the document for the input-output image table, now you can understand why, or maybe not why, but you can understand the numbering system a little bit better. We'll spend some go into detail of octal in another video. Well, here's another number system, hexadecimal base 16. And so notice this one. This one goes 0 through. This one's really weird because it goes 0 through 9. But then look at this. We've got letters in there, A, B, C, D, and then it starts to repeat. But we'll have to come back to that and explain that in another video, a later video. But the one I want to compare, we looked at decimal and we looked at binary. So binary base 2, remember the base tells you the number of symbols. In base 10, there's 10 symbols, 0 through 9. In base 8, there's 8 symbols, 0 through 7. In hexadecimal, the weird one, there's 16, 0 through, well, we go 9, and then, but we go 1, 2, 3, 4, 5, 6, that's 16. So this goes 0 through F, whatever that is. We'll have to talk about that. Well, in the base 2 number system, we're only going to have 2 digits, 2 symbols we use, and as you know, we can use a 0 or 1, and once we use up those symbols, we have to start to repeat. Notice that when we went through 0 through 9, once we went past the maximum number of symbols, down here we started to repeat. Same with base 8. We can go 0 through 7, and then we start to repeat. And over here, again, down here we start to repeat. Well, base 2, we can use a 0, we can use a 1, and once we're done with that, then we got to start to repeat. So I change this to a 1, This is a 0. This is a 1. Then I can add another 1. And then just the process starts all the way over. You can see how this builds up into a very, 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 very large number of bits. So when I come down here, if I compare these, this is a 20, that's a 24, that's a 14 in base 16. Look at the number of bits I have here. So as I start counting over here in binary, the higher I count, the greater the number of bits I'm going to need. So I wanted you to look at this because I think this table shows clearly when you compare decimal to binary or machine language, you can see that, well, one thing you can see is I'm going to need a lot of room to store these bits. Once I start counting at really, really high numbers, I'm going to need a lot of bits to represent those numbers. So here's a comparison. So I'm going to switch back to the PowerPoint now, and then we'll talk a little bit more about binary. Okay, so we talked about base 10, 10 to the nth power. The 10 tells us the number of symbols. If I take the base minus 1, that tells us the value of the highest symbol in a particular number system. So we as humans, we use a base 10 number system. 10 minus 1 is 9. So the value of the highest symbol in the base 10 system would be a 9. So you want to remember that relationship. You want to remember two things here. The base tells you the number of symbols in a particular number system. Now the reason that's important is all number systems are going to be represented this way, and then on the exam I'm going to ask you to make up your own number system, and whatever you make up is going to be based on this information in this slide. So the base tells us the number of symbols. In a base 10 number system, there will be 10 symbols, and the base minus 1 tells us the value of the highest symbol. So 10 minus 1 is 9. You can see that there's 10 symbols, and the highest value here is 9. Well, what about a base 2? I will show that as 2 to the nth power. The 2 means I'm going to have 2 symbols, and the 2 minus 1, the base minus 1, tells us the value of the highest symbol. So if I have 2 symbols, 2 minus 1 is a 1, so the highest symbol in a binary number system would be a 1, and the 2 symbols I'm allowed to use would be 0 and 1. Now you'll recognize this slide in just a second. I'll use a term that you probably learned in grade school, but these boxes or cells just kind of help us to understand how these number systems work. So I want to talk about one that you're already familiar with. Before I get into that, these boxes, we're going to put symbols in here for number systems, but I want to show that, remember that when we start counting now with 0 instead of 1. So instead of this being the first cell, the fourth, the second, the third, the fourth, the fifth, this is the 0th cell. 0, 1, 2, 3, 4. We'll start counting, and all the time that we count now, we'll start with 0. So what we're doing now is counting the position of these numbers or cells. So this is the 0th position. This is the first position, the second, the third, and the fourth. Now, one advantage to doing this is that if we start counting, then this becomes, we'll call it right now, the position of the weight or the number that we're talking about. Eventually, this can become the bit position when we move to binary. But for now, since we're dealing with base 10, this position of that cell, if I write it that way, you learn this as place value. You know that in the decimal number, if I put the decimal point right here, then I have the ones place and the tens place and the hundredths and so forth. Well, if you start counting the positions with a 0, then what you can do is you can represent place value like this. You can represent the base raised to the power of the position. So this is the 0th position, so I can show this as 10 to the 0. This is the 1st position, so I can show this as 10 to the 1. So these numbers right here, if you start counting these positions with 0, then I can get the place values down here by just taking the base raised to the power of whatever that position is. 10 to the 0 is a 1, So this is the ones place. 10 to the 1 is 10. So this is the 10 place, the tens place. 10 to the second is 100. That's the hundreds place. Thousands, 10,000s, and so forth. So you learned that probably in grade school at some point, place value. Well, we don't really call it place value here. We say that each one of these positions has a weight. Each one has a weight. So this has a weight of 1. This has a weight of 10. This has a weight of 100, and so forth. So think about weights. So if let's say I gave you a decimal number. I gave you the decimal number 1024. So I got a 1, 0, 2, 4. What exactly does that mean? If I have 1024, so imagine in these boxes 1024, 1, 0, 2, 4. What that means is the 1 here, that means I have one of these things. 10 to the third is 1,000. So I got 1 times 1,000. That has a value of 1,000. So imagine I have 1,000. Write that over here. The next one is a 0. 0 times, well, this is 100. 10 to the second is 100. So 0 times 100 is 0. So I don't have any hundreds. So far I got 1,000. I don't have any hundreds. I got 10 to the first, which is a 10, but I got a 2 here, so 2 times that is a 20. And then I got a 4 here in this box. We said 1024, so I got a 4 here, and I got 4 times 1 is 4. So if I go 1 times 1,000, that's 1,000. This is 0, so I don't get anything there. I got 10. I got 2 times 10, which is 20. And then I got 4 times 1, which is 4. If you add all those up, you get the number we started with, 1024. So that's pretty simple. Place value. You learned about place value. Now, why am I talking about this if it's so simple? Well, the reason is it's easy when you do it in base 10. But remember, computers store everything as a binary number or binary code. Well, one reason for that, we talked about the digital advantage. All information is stored as a number. So if you start to reproduce, or I should say to copy the information via the video, audio, a picture, the original and the copy look exactly alike because all we're doing is reproducing numbers. And so keep that kind of in the back of your mind. The other advantage to digitizing information is that we can compress the information. We can take a lot of information and fit it on a very, very small space. That's part of that digital advantage that we talked about. And that kind of put that on your mind to think about that as we go through this. Now I want to move on to binary. This is machine language. This is what digital devices understand. The binary number system. The word binary, that means 2. So we have a number system that deals with basically 2 symbols. This is a base 2 number system, as I said before. The base tells us the number of symbols, so we can only use 2 symbols. If I take the base minus 1 in any number system, it tells us the value of the highest symbol in that number system. So I have a base 2 number system. We can use 2 symbols. If I take 2 minus 1, I get 1. So the value of the highest symbol in that base 2 number system is a 1. That means I can only use symbols 0 and 1, and that's binary. Well, you know from previous discussions that we can represent binary information easily inside of a machine. Remember, machines only understand current and voltage, so the 0 and 1 is just an abstraction for us as humans to understand. The 1 represents the presence of a voltage, and the 0 can represent the absence of a voltage. And for us, we said we're going to use the ideal value of 5 volts and 0 volts. So you can see here I have a digital waveform, and this digital pulse could represent Goes from 0 to 5, could represent a high or a 1. And this represents a high or a 1. And over here I have a 0. So I could have a 1, 0, 1, and so forth. So we can use voltages to represent digital information. This is that two-state electronics that we talked about. We can use any two voltages. I can use 15 volts and 10 volts if I want to. I can use a 15 to represent a high and a 10 to represent a low. It doesn't matter which value you use, but for our purposes, we're going to stick with the plus 5 volts to represent a binary 1, or what we call a high, and a 0 volts to represent a binary low, or a 0 value in binary. Now let's talk about PLCs and binary. Some of this is review, but I don't think you can hear this stuff enough. You know now that a binary digit, that's kind of a contraction of the B from the word binary and the IT from the word digit, and we put that together to form the word bit. So a bit is a binary digit. A bit is a 0 or 1. Now, in the microprocessor contains thousands and thousands of locations called registers. Now, we talked about this last week in lecture. We talked about something called the shift register. A register is a physical device that stores bits. It stores zeros and ones. And I think I mentioned in that lecture that you can actually order devices called registers. If you were into computer science or electrical engineering, you might build some kind of digital device and you might have to store that information. Well, you can store it in the register. You can actually go buy a device called a register, wire it into your circuit, and if you know what you're doing, you can move bits into and out of those physical registers. But what I want to do here is I want to draw a parallel between this idea of a register and something called a word. Now, what I'm going to tell you is only correct for the purposes of this class. Outside this class, what I'm going to tell you is not true. What I mean is a register is a physical device that you can buy it, you can install it on an electrical circuit, and you can use it if you know what you're doing. But here it says registers are also called words, and that's not really true. We're going to, for the purposes of PLCs, we're going to call register words. But a register is a physical device. A word is a virtual logical structure. It's just something that exists in memory. You know, we talked about a bit being a 0 or a 1. We mentioned the term byte. A byte is 8 bits. Well, a word is a certain number of bytes or a certain number of bits. And it's not fixed. A word is machine dependent, meaning that whoever designs that machine, they design or they determine how big a word size is going to be. You could have a word size of 1 byte. You can have a word size of 4 bytes. You, as the designer of the machine, can pick and choose how big you want your word size to be, and there are advantages and disadvantages to having a large word size that we won't go into right here. But for the purposes of this class, we're going to assume that registers and words are the same thing, and that's going to be important. That's going to have important ramifications when you actually use the simulation software, or when you actually use a PLC. Knowing the word size is going to be important because it's going to determine the number of connections you can make to an input module or output module. But we'll have more about that later. And so it says each word stores data as bits. So if you can imagine a word for us is going to be 16 bits or 2 bytes. For our class, remember, in reality, a word is machine dependent. But for the purposes of our class, a word is going to be 16 bits or 2 bytes. Well, each bit position on the 16 can store a 0 or 1, and each individual 0 or each individual 1 can represent information or data. For example, if I have a word, a 16-bit word, and think of the 16th bit if you want. It can be a 0, it can be a 1. Maybe if it's a 1, it represents a switch that is closed. If it's a 0, it represents a switch that's open. I can use it to represent that information, that's data. That bit position can represent a relay coil that's energized or not energized. Maybe if it's energized, it represents a 1. I can show that as a 1. If the relay coil is not energized, I can show that as a 0. So I can use individual bits to represent data or information. I can also represent groups of bits to represent data or information. And we'll talk about that at another time. So here it says the number of bits in the word depends on the type of PLC. Well, that just goes back to what I said earlier, that the word size or the number of registers used to represent a word is machine dependent. That depends on who makes the PLC or the digital device. They have say-so over how big they want to make their word size. 8-bit and 16-bit words are most common with PLCs. 8 and 16 are common. Let's look at a word in more detail. So here is a 16-bit word. We're going to break it down and talk about parts of a word. First, I want to point out that the far end here, I have the far left bit, and then I have the far, well, this is the far right bit and the far left bit. The far left bit, MSB, that stands for most significant bit. The most significant bit. And the LSB is the least significant bit. Now, let me start by saying that that's not fixed. If I wanted to, I can switch these around. I can make this the most significant bit, and I can make this my least significant bit. But just to keep it simple, we'll keep it the way it is in this diagram. It's important if you're dealing with a number that you understand and know which is the MSB and which is the LSB. Let's go back to my example when we talked about the decimal number 1024. Let's say I had $1,024. $1,024. And then I think about the most significant number in that list of numbers, that group of numbers, and the least significant number. Well, the most significant number, the one that carries the most weight, will be the 1,000. I have a 1, which represents 1,000. I have a 0, which doesn't represent anything because I have a 0 there, and there are no hundreds. Then I have 10, and I have ones. Well, the leftmost number, the number 1, represents 1,000. The rightmost number, the number 4, represents ones. So I have 1,000, and I have 4 ones. The leftmost number is obviously the most significant one. It's the most important one. If you had to lose pieces of that number, if say it was that money that you put into your pocket, you'd much rather lose the $4 than you would the 1,000. Well, it kind of works the same way here. Once you identify which bit is the most significant bit and which is the least significant bit, the most significant bit carries the most, we'll say the most weight. The least significant bit carries the least amount of weight. And you'll understand more when we get into actual numbers, binary numbers. You'll understand more about what I mean. I'll bring this back up, the most significant bit and the least significant bit, and you can understand it. So here's a word, a 16-bit word. We already talked about the LSB and the MSB. We can also talk about the upper byte and the lower byte. We can look at the number of bytes. In the 16-bit word, a byte is 8 bits. And so we have 8 and 8. We have a lower byte and we have an upper byte. So I can refer to the most significant bit. You know I'm talking about this one. I can refer to the least significant bit. You know I'm talking about this one. I can talk about the upper byte. You know I'm talking about the left side of this, the left 8. I can talk about the lower byte. I'm talking about the right side of this, or the right 8. And each one of these cells, it's impossible to have an empty cell. If this is a register, remember for us a register and word are one and the same. If this is a register, then if it's powered up, then it's got to contain something. You can't have an empty cell in the register. It's got to hold a 0 or a 1. So here, this is showing a bit in one of the cells of the register. Now you might think about that and say, well, what do you mean it's got to have something in there? What if I don't put anything in there? Well, there's always going to be either 0 volts or 5 volts. So here's how we think about that. If you put it in there, we call that data. If you put the 0 or 1s in the register, we call it data. If you didn't put it in there, we call it garbage. How could you size memory? Since we're talking about bits and bytes and words, how could you size PLC memory? And this will be something that you actually have to do for me on the exam. So if you're taking notes here, you definitely want to mark the slide. This slide is one to mark. So if you know that memory size is, now you got to pay attention to what we're talking about here. This is 884 words, not bytes, but words. So if the memory size is 884 words, and you know the word size is 16 bits, and I want to know, okay, how many individual pieces of data can I store? It's just a multiplication problem. I have 884 words. Each word is 16 bits, so I go 884 times 16. I can store 14,144 pieces of data. If, on the other hand, the word size is 884, or I have 884 words, not the word size, I have 884 words, and a word size is 8 bits, well, do the same process here. One word, I'll have 884 words times the word size is 8 bits. If I take 884 times 8, now I can only store 7,072 individual pieces of data, individual zeros and ones. So knowing how to size memory, how to determine how many zeros and how many ones can I store, turns out to be pretty important. So remember this calculation. Now I can change this if I wanted to. We'll talk about kilobytes. I think we might have already in the previous lecture talked about kilobytes. Remember there's kilobits and kilobytes. The word kilo is important because if I'm talking kilobytes, then that kilo has a certain value. If I'm talking kilobits, it has a different value. The way you tell the difference is kilobytes, the K is followed by a capital B. Kilobits, the K is followed by a lowercase b. But the kilo, normally to you as an engineer, kilo means 1,000. And it's the same thing with kilobits. You have kilobits, a kilobit is 1,000 bits. But when you deal with kilobytes, it's different. A kilobyte is 1,024 bits or bytes. A kilobyte is 1,024 bytes. So you want to make sure you're clear on that. That if I change this to kilobytes, then I got a different math problem here. So kilobytes, KB, kilobytes. I have to figure out how many. If I have 884 kilobytes, then I have to figure out a kilobyte is 1,024 bytes. So I'm going to multiply the 884 times 1,024 to get the individual bytes. And then you know a byte is, 1 byte is 8 bits. So I have to multiply that by 8 to get the number of individual pieces of information that can be stored. So you want to at some point go back and look at the slide where we talked about kilobytes. We can forget about kilobits. I won't say too much about that. But kilobytes, and if I add that to this, then that changes the math a little bit. And you want to make sure you understand how to handle kilobytes. If I ask you to size memory, or if I ask how many pieces of information can be stored, you want to review that. So when comparing PLC systems, you got to know the number of bytes per word to determine the capacity of the system's memory. That's the importance of that. And so here, It says normally PLCs do not require storage above 128. Now notice kilobytes. In many cases or many instances, we only need a memory of 1 or 2 kilobytes. So remember, a KB, a kilobyte, kilo 1024. So it'll be 2 times 1024. That will give you the number of bytes. And then if you want the individual bits, you take the product of that, 2 times 1024 to get the number of bytes, and then you have to take that and multiply by the number of bits for each byte, and that'll tell you the number of individual pieces of information you can store in memory. So here's another slide just to kind of help you remember when you're reviewing for the exam. Come back and look at this slide and make sure you understand the difference. If you don't, please ask me and I'll schedule time. We can go over some more of this stuff. Now, how do you convert binary to decimal? Binary to decimal. Well, that's important because we talked about two very important number systems, base 10 and base 2. We as humans, we are accustomed to, we use base 10. Machines use base 2, so we got to be able to go from one to the other. So what I have here is this we call 8421 code. So right here, this is the place value. This is place value for base 2. So if you remember in the previous slide, if we take the base to the bit position, this will be 2 to the 0. This will be 2 to the first, 2 to the second, 2 to the third. That gives us the weight of each position. So 2 to the 0 is a 1, 2 to the 1 is a 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16. I can keep going if I wanted to, but here we're just dealing with 4 bits. So I have this number right here. Now remember, this is binary in the box here, so I can only represent zeros and ones in the box. I have a binary number 0, 1, 1, 0, and I want to convert that to decimal. And so this is 0, 0 what? 0 of these. I don't have any 8s. I got 1, 1 what? 1 of these. I got 1, 4. I got 1, 2, and I don't have any 1s. So if I take a 4 and a 2, I add those together, I get a 6. And so down here, I get that the binary number 0, 1, 1, 0. Now notice a little 2 here. I got to show what base I'm in, and the way I do that now is I subscript this with whatever base this is. This is the base 2 number. So the binary number 0, 1, 1, 0, this is binary, is equal to 6 in our number system, base 10. So when you enter on your cell phone, you enter 6 on your cell phone. Say you're going to dial a number 641. Well, when you enter 6 and push the keypad, this is what you see echo to the screen of your cell phone. But this right here is actually what goes into your cell phone. This is what we call machine language. And remember, the 0 and the 1s just represent the presence or absence of voltages. But we can here code this information now. This number 6 as a 0, 1, 1, 0 base 2. Alright, so that's converting binary to decimal. What if I want to go the other way? I want to convert decimal to binary. Well, that's pretty easy. Just remember your 8421 code. So these are your decimal weights for each of those binary numbers. So let's say I have I got a 1 and a 1. I got we want to convert the binary number 12, decimal number 12 to binary. So how do I go from a decimal 12 to binary? Well, I got a 1 and a 1. I want to start with the most significant bit first. What you're doing is you're taking the biggest weight out of the number that you have here and seeing what's left. So for example, the biggest piece of this that I can take out of a 12 this weight over here that the binary number can have is an 8. So if I have, let's say I have 12 and I take away 8, I only have 4 left over. Well, here in the 12, I'm showing I have 1 8 and I have a 4. I add those together, I get 12. So I don't have any 2s, I don't have any 1s. So I'm going to represent 12, a decimal 12, as a 1 1 0 0. Notice here I have a 1 2. I have to show what number system I'm in. This is critical because I'm going to have other number systems I'm dealing with. How you know this is not base 8 or base 16? How you know you're in base 10? The way you know which base you're in is by having, I got to subscript this. This is a 1, that's a 0, so it's 12 base 10. And in base, how do I know that's not 1100? How do I know that's a 1100? Because I have that subscript of a 2 there. But the point here is, to us as humans, if I want to represent the number 12, I just write down 1 2. That's our number system. If I want to represent that same number 12 in a machine, it doesn't know anything about 1 2. It doesn't even know what a 2 is because it can only have a 0 or 1. The way it's going to represent the number 12 is going to represent that in binary as a 1 1 0 0. Here's another way, though, I can convert a decimal number to binary. This is called the repeated division method. And it's pretty simple. All you're going to do is take the number you want to convert, the decimal number you want to convert. You're going to keep dividing that number by 2. And sometimes you're going to end up with a remainder. Well, actually, you'll end up with a remainder all the time. But I should say, you'll end up with a remainder of either a 1 or a 0. And that remainder becomes the binary number that we're looking for. But what you got to remember is, I have it right here. It says perform series of divisions by 2. If there is a remainder, place a 1 in that bit position with the LSB. If there is no remainder, it's a 0 in that position. So when you do the division, say you're going to divide 47 by 2. You're going to keep dividing by 2. You get 23 with a remainder of 1. So that remainder of 1 becomes part of your binary number, is what this is saying up here. The other thing this is saying is the very first number you get, that's your LSB, your least significant bit, not your most significant bit. So if we run through this, if I take 47, divide by 2, I get 23, remainder 1, then I get a 1 here. Now I take this number, divide by 2. I just keep taking whatever I get as an answer for my first division and keep dividing that by 2. So I divided this by 2. I got 23 with a remainder of 1. That becomes my binary number. Now I take this number, 23, divide that by 2. I get an 11 with a remainder of 1. That becomes my second binary number. I keep doing that. I take this number, 11, divide by 2. I get a 5 with a remainder of 1. I take this number, divide by 2. I get a 2 with a remainder of 1. So there's my remainder. Now look right here. I got a 2 divided by 2. That's a 1 with no remainder. So I put no remainder means I have a 0 here. And then I got a 1 divided by, I got a 1 divided by 2. Well, this one's a little tricky. So I'm actually going to show this, even though I'm doing it in PowerPoint. I'm going to actually do this one in live because I'm going to stream this lecture as well as give you this PowerPoint presentation. I'm going to do that for these number systems because this is so important to what we're doing. You got to understand number systems and you got to understand code. So you'll get a double dose of this. You'll have the actual video for the PowerPoint that I'm preparing now, but you'll also get a live lecture where I'll actually run through basically the same information in the PowerPoint, but I think when you see it live, it'll probably make a little bit more sense to you. And so this will be one of the examples that I'll go into. And then I want you to be careful about getting that last digit right there, that 1 divided by 2 with a remainder of 1. It's going to be 1 divided by 2. It's going to be 0, but you're going to have a remainder of 1. But again, watch my live stream and you'll see how we ended up with that 1. But to make a long story short, a 47 in our number system to a computer looks like a 1 0 1 1 1 1 base 2. You put in 47, you hit enter. What goes into the machine is this. What's reflected to the screen, if you have a screen, is this. For us, 47. For the machine, 1 0 1 1 1 1. Well, all right, this brings up something pretty interesting. If all I can use to represent binary information is a 0 or a 1, then what do I do? How do I represent negative numbers? I mean, if I have let's say a base 10 number 5, I can represent it with a plus sign in front of it, plus 5. I can represent it with a minus sign in front of it, minus 5. I can represent easily negative and positive numbers with the plus sign and the negative sign if I'm dealing with a base 10 number. But how do you do the same thing in binary if everything in binary can only be represented by 0 or 1? How do I represent a plus sign if I have zeros or 1, or a minus sign if all I have is zeros or 1s? Well, the answer is you can't have a minus binary number. You can't put a minus sign in front of, like, if I have 1 0 1, I can't have a minus 1 0 1 because the minus sign itself doesn't make sense to a computer. So it's not possible to use the plus sign or the minus sign because all data is represented by numbers in the machine. So how do we get around that? And it turns out there's 3 ways to represent negative numbers, and we're going to talk about all 3 ways. The first way is to use what we call a sign bit, and we'll go over that. The second way and the third way is kind of mathematical. There's this thing called a complement, and there's 2 types of complements. There's a ones complement and there's a twos complement, and we'll actually talk about both of those, and we'll use the ones and twos complement in another presentation. But you want to know what they are. So mark this slide. Make sure you're clear that there are 3 ways to represent negative numbers in binary. So we're going to talk about sign bits first. Sign bits are pretty easy. What happens is with a sign bit, let's say I have decimal values here. My range here is from plus 5 to minus 5. So I got all these numbers. I want to show a plus 5 in decimal. I want to write that in binary using binary numbers, but I want to be able to distinguish that from a minus sign, a minus 5. And the way you do that is use something called a sign bit. Now, the sign bit, normally if you see a binary number, you know the most significant bit is the leftmost bit. So the most significant bit here would be the leftmost bit. And the most significant bit here would be the leftmost bit. This most significant bit is a 0. This most significant bit is a 1. That's not true though if you're using a sign bit. If you're using the sign bit, the actual number, if you notice the magnitude of the number, you don't count that leftmost bit. That's going to be your sign. The actual number is the first 3 bits, and so my most significant bit will be here. For each of these, it's the 3rd bit over. So this is my most significant bit. This is my most significant bit. This will be my most significant bit here. The leftmost bit becomes your sign bit. If the number is positive, then that sign bit will be 0. If the number is negative, that sign bit will be a 1. So if you go here and think about your 8421 code, think about that. If this is a 101, so remember this will be 8421. Those are our weights, our 8421 code. That means I have right here I have a 4 and a 1, which is a 5. So here's my 5. And to show that that's a positive 5, I got a 0. So I know from that sign bit that that's a positive 5. Whereas down here, I got the same thing. Here's my magnitude. So I have, again, I have a 4 and a 1. So that's my 5. But to get that negative sign to show that it's a negative number, well, this is my sign bit here. So if you just walk into a room and you see this on the board, you see, let's say you see a 1, 1, 0, 1. I got to tell you that this number is used as a sign bit, so you know that this is not your most significant bit, that your most significant bit actually is here, and then from here over starts the actual magnitude of your number, and that leftmost bit is a sign bit. I have to tell you that. You got to know, if you're looking at just zeros and ones, and I tell you these are numbers, you got to say, hey, are we using the sign bit or not? And if I say, yeah, you're using the sign bit, then you know your most significant bit is not your leftmost bit, it's the one next to that over here. So that's one way, sign bits. Another way to represent a negative number is called a complement, a ones complement. And ones complements are really simple. All you do with a ones complement is you flip the bits. So, for example, if I have the binary number 1, 1, 1, 0, 1, and I want to find the ones complement of it, all I do is flip the bits. So I want to go from here, 1, 1, 1, 0, 1, base 2. The ones complement, I change what's a 1 to a 0, and what's a 0 to a 1. I just flip the bits. So 1, 1, 1, 0, 1 becomes a 0, 0, 0, 1, 0. Wherever I have a 1 over here, I change it with a 0. Where I have a 0 over here, I change it to a 1. So that's really simple. Now, I'm not showing you how to do anything with this yet. We'll get to that later on. We'll do something with this. But I just want to show you how you would take the ones complement. So we have sign bits to represent a negative number. I can also use a ones complement to represent a negative number. And then there's another way called a twos complement. A twos complement. Now, if you get on YouTube and you look up twos complement, they'll show you, there's a couple ways to get the twos complement. I'm going to show you the way I like to do it, which is what I have in this slide here. So I have it here. The way I like to do it, start at the right and write down the bits as they are up to and including the first one. Take the ones complement of the remaining bits. So what do you mean by that? Oh, here's what I mean. Here's a long list. This is a binary number. Number 1, start at the right and write the bits as they are up to and including the first one. So in other words, we start over here at the rightmost bit, and I go all the way over to my first 1, and I just leave those alone. I don't change anything. So from here all the way to my first 1, I leave those as they are. But everything after that first 1, I take the ones complement. So if I got a 0, I change it to a 1. If I have a 1, I change it to a 0. So up to and including the first 1, leave it alone. And everything after that, take the ones complement of it, put it together, and you got the twos complement. Now I think there's another way on YouTube. They'll probably say take the ones complement and add 1 to it. That works too. But I think this way is easier and faster. But you can do it any way you want, so long as you know what the twos complement is and you can give me the correct twos complement. So that's it for this video. Now, as I said before, this is so important that not only are you going to get this video, but I'm also going to do a live stream. So please watch this video, and I know it's a double duty for you guys, because it's 2 hours instead of 1. But this is really important stuff. So watch the video. I think if you watch this video and then probably you watch this one first and then you watch the live stream, it'll probably make a little bit more sense to you. So guys, have a great rest of the day, and I will see you soon.